Setting up hypothesis test, example 2. Some people think that home teams might have an advantage over visiting teams because home teams don't need to travel and because home teams have the home crowd cheering for them. If there's a home advantage, they expect that in the long run, home teams would win more than half the time. An example of n equal 80 NBA basketball games, the proportion won by the home team, p hat, 50 out of 80. 50 divided by 80 is 0.625. And we wanted to test whether this provides sufficient evidence of a home advantage. So this diagram illustrates the relationship between the sample proportion and the population proportion. So our sample proportion is 0.625. That's taken from a larger population where we don't know the proportion of games that would be won by in the long run. And we want to compare it to the proportion won by the home team in the long run if there's no home advantage. So that'd be 0.5. So that's what we want to compare it to. Okay, so that means we want to test H naught. P is equal to 0.5. There's no home advantage. Versus H1, P is greater than 0.5. There is a home advantage. So this is what's called a right-tailed test. So H naught, H0, or H naught usually has an equal sign in it, or if not an equals, at least something that includes equals, like a greater than or equal to symbol, or less than or equal to symbol, and in reverse of whatever H1 is. Population proportion P represents the proportion of games that would be won by the home team in the long run, and in this case is unknown. The null value, that's the value of P if H naught is true, it's going to be 0.5. The other null value, that's the proportion that would be lost by the home team. 1 minus 0.5 would be also 0.5. That's represented by Q0. Alternative hypothesis or the research hypothesis, you'll see the notation H1 or HA representing what we're trying to prove, and it has either a less than symbol, a greater than symbol, or a not equal to symbol. So this is a left-tailed test, right-tailed test, or a two-tailed test. Our sample size in this case is 80. Our sample proportion, 50 divided by 80, would be 0.625. X is the number of games won by the home team, that in this case it's 50. This is called a binomial random variable. It's binomial because each team has two possible outcomes, either win or lose. And it's a random variable because the number of games won can vary randomly from one sample to another. Before testing hypotheses, it's common to establish the level of confidence, often 95% or 0.95. So we'll take, for this example, we'll use 95%. So 1 minus alpha is 0.95. Greek letter alpha is 1 minus 0.95 is going to be 0.05. That's our level of doubt. It's actually called the level of significance, but I like to call it the level of doubt. It's represented by Greek letter alpha. Okay, so we want to check to see whether we can use the z-table as a shortcut to test these hypotheses. So we want to test whether n times p0 and n times q0 are both at least 5. So we have 80 games. 80 times 0.5 is 40, and that's bigger than 5. And Q0 is also 0.5. 80 times 0.5 is 40, greater than or equal to 5. So they're both at least 5. So that means we can use the z-table. So the mean of p hat, if H naught is true, then on the average we expect the home team to win 50% of the time, or 0.5. Standard deviation of p hat, square root of p0 times q0 over n, square root of 0.5 times 0.5 over 80, and that's equal to, we put that in the calculator, 0.0559 0.1699. And then we compute the test statistic. It's basically a variation on the z-score formula that we had before earlier in the semester. Score minus the mean divided by the standard deviation. In this case, the score is going to be our sample proportion, which is 0.625. The mean of p-hat is 0.5, and the standard deviation 0.0559 0.1699, and it comes out to be approximately 2.24. The formula can be abbreviated. You can leave off the zeros. The zeros kind of make it clear that what we're putting in for p are the null values, but often it's just written without the subscripts, but it's understood that you want to put in the null values. So you can write as p-hat minus p without the zero on the end, and so forth. But in any case, you get a test statistic of 2.24. And then we want to look this up in the z-table now, the next step. And this is because we're doing a right-tailed test, and because our z-table is left-tailed, we want to look up the opposite sign. So we want the probability of z is greater than 2.24. So that's on the bell curve, 0 is in the middle, 2.24 would be on the right side, but we have a left-tailed table, so we're going to look on the left side of the table, so this is going to be, because the bell curve is symmetric, it's going to have the same probability. So we're going to look in row negative 2.2, column 4 of the z-table, and we get a p-value of 0.0125, and that means that's less than alpha, less than 0.05. That means we can reject H0 with 95% confidence and conclude that there is a home advantage. There's Triola has what he calls a range rule of thumb, part 2, and that says that for, any test statistic more than 2 will provide enough evidence to reject H0. So our test statistic was 2.24. That's more than 2. So even without going to the table, just looking at the test statistic, that tells us that there's enough evidence to reject H0. We compared our p-value to alpha with 0.05. If we want to lower our chance of making a type 1 error, we could have used alpha equal 0.01 or alpha equal 0.001. If we use alpha equal 0.01, our p-value is more than alpha, so that means we would fail to reject H0 at that level of significance. So it depends on how much of a chance we want to make of making what's called a type 1 error. Technically, we never accept H0 because it might be a larger sample, would provide stronger evidence. So technically, either we reject H0 or we don't know. Some researchers simply report a p-value without specifying alpha. Generally, the lower the p-value, the stronger conclusion. Our p-value was 0.01. It's between 0.0125, so it's between 0.01 and 0.05. So we had moderate evidence of a home advantage. Okay, so this chart here has some of the terminology of hypothesis testing. Either H0 is true or H1 is true. Either we don't reject H0 or we reject H0. There's two of these are errors. So if we reject H0 and H0 is true, that's called a type 1 error. If we don't reject H0 and If we reject H0 and H0 is true, it's type 1 error. If we don't reject H0 and H1 is true, that's called a type 2 error. So in this case, we rejected H0, so we took a chance of making a type 1 error. Either way, you take a chance of making some type of error. 1 minus alpha is our desired level of confidence. The Greek letter alpha is our desired level of significance. I like to call it the level of doubt. The probability of making a type 1 error. P-value is our actual level of doubt. That was the 0.0125. Greek letter beta is the probability of a type 2 error, and that's usually not computed. You need to make additional assumptions. We will not be computing the probability of a type 2 error. 1 minus beta is the power of the test. So in this example, is it possible we made a type 1 error? In example 2, yes, because we rejected H0. And if it's possible to make a type 2 error, no, because we rejected H0. If we reject H0, we take a chance of making a type 1 error. If we use alpha 0.01 instead of 0.05, we might have made a type 2 error. Because at that point we would have, if we have alpha equal 0.01, we would have failed to reject H0 and take a chance of making a type 2 error. And you can lower the chance of making either type of error by increasing the sample size. The drawback there is that the larger samples are more expensive. And that concludes this presentation.